Okay, this is Calculus 2. This is the third video of the series. We're going to be looking at Reimanns Sum, definite integrals, and of course the most important thing, the Fundamental Theorem of Calculus. So here we go. Okay, so we're going to compare Reimanns Sum versus a definite integral. So we've seen Reimanns Sum before. We know that the Reimanns sum is simply finding the area under the curve using a sum of rectangles with a fixed partition, with a fixed width. And we saw this in the previous video where I showed you how we found or how we approximated the area underneath the curve using a number of rectangles and of course using what we call the limit process. So this is Reimanns sum. And if you look carefully at it, and if you watch the last video, you'll notice that this is how we approximated or actually found the area underneath the curve. Now, we also looked at what we know as the lower sum and upper sums. That's where that capital MI and that little mi came into play. Well, it's also known as the left Reimanns sum and the right Reimanns sum. However, what we're trying to do is we're trying to get away from the limit process and we're trying to find a much faster way to be able to find the area underneath the curve. And that's where definite integrals come in. So it's finding the area under the curve using, of course, what we know of as integrals. Now, this is the formula. Now it changes a little bit. The first formula said n approaches infinity, and now this we have the norm of delta x as it approaches 0. So that's the part that changes a little bit. So let me explain this to you. All this means is that my partitions are not constant. In other words, my rectangles have different widths, and as those widths approach 0, then eventually we could find the area underneath the curve. And all of this can be replaced with the definite integral, f of x dx, as it goes from a to b. So a is my lower limit and b is my upper limit. So using this formula now, we're able to find the area underneath the curve much quicker than the limit process that we did before. So just to repeat, the indefinite integral is the family of antiderivatives. That's the plus c part. So we just found the antiderivative. But what the definite integral tells me to do, it allows me to actually find a value. Okay. So this is what evaluating a definite integral looks like. So we have our function, in this case it is x cubed, dx of course with respect to x, and we have our upper and lower bound, in this case it's from 0 to 1. So what this does, it allows me to replace the limit process. So the entire process that we did in the last video, where we're trying to evaluate or find the area underneath the curve, well, that can be replaced simply with this definite integral. Now, how do we evaluate a definite integral? Well, this is it. We use this very important theorem called the Fundamental Theorem of Calculus. The Fundamental Theorem. It's got to mean something. Okay, so this is extremely important for Cal 2. And this is what it is. So if a function f is continuous on the closed interval from a to b, and f is an antiderivative, well, we know the capital F is an antiderivative, then the following statement is true. So the definite integral of f of x dx from a to b is simply f of b minus f of a. So what does f of b minus f of a mean? Well, we simply take the upper bound, in this case b, and evaluate the antiderivative with that value, and subtract it with the lower bound evaluated into the antiderivative. And when we subtract these two values, we end up with a value, and that is how we evaluate a definite integral. So we evaluate the antiderivative using the endpoints a to b. And more importantly, or the most important thing is to understand is that a definite integral can either be negative, positive, or 0. So in other words, whenever we evaluate a definite integral, it's possible to get either a negative value, a positive value, or simply 0 as a value. However, if we're looking to find the area, then the function must be non-negative within that interval. So what does it mean to say non-negative? Simply means the function needs to be above the x-axis. So as long as it's above the x-axis, then I can use this formula to evaluate or to find the area underneath the curve within a certain interval. So let's take a look at this example from the one above. So we have the definite integral of x cubed between 0 and 1. Okay, so let's forget there's the upper and lower limits. What do we do with the integral of x cubed? We simply find the antiderivative. So when we find the antiderivative, we get x to the fourth over 4. Now previously, in the other videos, we would add that plus c, that plus constant. But we don't need that to be able to evaluate the integral. So we simply use x to the fourth over 4. And we evaluate it between 0 and 1, where 1 is the upper limit and 0 is the lower limit. So I simply replace 1 into my antiderivative and evaluate 1 to the power of 4 over 4 minus 0 to the power of 4 over 4. And when I evaluate this and simplify this, I get 1/4. So 1/4 is the value of this definite integral. However, because it is non-negative, then 1/4 is also the area underneath the curve for this function x cubed between 0 and 1. Okay, so let's take a look at some properties of indefinite integrals. These are extremely important. If we take a look at the first one, f of x dx, as a goes to a is equal to 0. Well, it's normal. A goes to a means it doesn't go anywhere. So there's no gap, there's no space, so we can't find the area underneath the curve, and therefore we cannot evaluate this. So what is the area between nothing? Well, it's nothing. So for example, if I were asked to find the definite integral of sine x dx from pi to pi, well, it would simply be 0. Now remember, when we're evaluating any trigonometric function, it is extremely important that your calculator is in radian mode, okay? Because all the values will always be in radian, even if they're values like 1, 2, 3, and so on, okay? So make sure that whenever you're evaluating any trigonometric function, it has to be, your calculator needs to be in radian mode. The second property, if it happens to be b to a, so in other words, your lower limit is larger than your upper limit, well, then you need to change that. And how do you change it? By simply putting a negative in front of the integral and changing your upper and lower limits. So your lower becomes your upper and your upper becomes your lower. So for example, from 3 to 0, well, my upper limit is usually larger, but in this case it's smaller than my lower limit. So I can rewrite this equation or this integral by putting a negative and changing my upper and lower limits and making the lower the upper and the upper the lower. The third property, I can break this up, and this happens very, very often with absolute value integrals. So a to b, I can go from a to c and then from c to b. So I can break it up, and I'll give you a couple of examples after where you'll understand how these work exactly. So for example, the absolute value of dx from -1 to 1, well, because we all know what the absolute value of x looks like, we know that from -1 to 0, it's negative x, and then from 0 to 1, it's positive x. So we need to break it up into two parts to be able to evaluate the definite integral or to find the area underneath the curve, in this particular case, between -1 and 1. But I'll do a more specific example in the next slides. So this is what it looks like. So if we take a look from -1 to 0, I have the negative slope, and then from 0 to 1, I have the positive slope. So I would break it up into two parts to be able to evaluate or to find the area underneath the curve. A definite integral can be negative, positive, or 0. To find the area, the function must be non-negative. So as you can see for this last graph that I put up, the function is non-negative, meaning that it's above the x-axis. But if we take a look at this one, we can see that the function, for example, half of it is below the x-axis while the other half is above the x-axis. So in this particular case, we would not technically find the area underneath this curve. What we would be doing is simply evaluating the definite integral, in this case from -1 to 1. Okay, the fourth property is when we're multiplying a constant times a function. What we can simply do is just factor out the constant, evaluate the definite integral, and then multiply the constant back into the function. And finally, the last property is if we have an addition or subtraction of functions, we can simply break up the definite integral. So these are the 5 properties that we should know for evaluating definite integrals. And let's quickly sum up, what we're trying to do. So there are 2 methods for finding area. There's the limit process, which we've done in previous videos, that long process of choosing the right end or the left end, determining the number of rectangles and trying to approximate the area underneath the curve, or actually finding the area underneath the curve using the limit process. But we're trying to move away from that, And what we're going to replace this method with is definite integrals. And how do we evaluate definite integrals? Using the Fundamental Theorem of Calculus. So let's take a look at some previous examples done in other videos. So we did this in the last, or we evaluated this last function in the previous video, and we used 6 rectangles, and we used the limit process to be able to approximate the area. And when we did so, we found the area to be 12.33. Now we're going to use a definite integral. Now we know that the upper limit is 4 and the lower limit is 2 to the 4, and we have our function 9 minus x. We simply find the antiderivative. We evaluate f of b minus f of a, meaning that I'm going to replace x with 4 and then subtract it with x being 2. So I end up with 36 minus 8. That's when x is 4, minus 18 minus 2 when x is 2. So there's my f of b minus f of a. When I evaluate this, I end up with 12. 12 is the area underneath the curve for this function 9 minus x between 2 and 4. Another example that we've also seen in the previous videos is this one, 4 minus x squared between negative 2 and 2. Well, for this one, we also used the limit process, but we left n as n. We didn't choose a number of rectangles. And when we worked it out through the limit process, we found the area to be 10.67. Well, using definite integrals, I set up this type of equation. I get 4 minus x squared dx between negative 2 to 2. I find the antiderivative of 4 minus x squared, which is 4x minus x cubed over 3, and I evaluate this between negative 2 and 2. Once again, my lower bound a is negative 2, my upper bound b is 2, f of b minus f of a, and end up with 32 over 3. And what is 32 over 3? 32 over 3 is 10.67. Much quicker way to find the area underneath the curve than the limit process. Okay, so definite integrals with absolute value functions. So we're going to take a look at how we use the properties to break up specifically for absolute value when we're trying to evaluate a definite integral using absolute value functions. So we have this function, the absolute value of x minus 3 from 1 to 4. And you can see the picture, and you can see that the vertex is 3 and 0. So what you should notice is that between 1 and 3, the slope is negative, and between 3 and 4, the slope is positive. So because the slopes are different, what we're going to do is we're going to break up this definite integral into 2 parts. So from 1 to 3, we have the negative slope of the function, and then from 3 to 4, we have the positive slope of the function. The second example is 3 minus the absolute value of 3 minus x. And going back to what you did in secondary 5 or even in pre-cal, the vertex of this function is 3 and 3. So what we're going to do is we're going to use those properties, and we're going to break this up once again into 2 parts because I need to evaluate the absolute value once again. And here we have the absolute value of x minus 3 between 1 and 4. So we're going to evaluate the first part, which is simply the definite integral of 3, and then the second part, which is the definite integral of the absolute value of x minus 3. At this point, we completely forget about the graph that we drew, and now we have to think once again, well, there's the negative slope and the positive slope for the absolute value of x minus 3. So we would use the properties, and we would break it up this way to evaluate. So the next slide, I'm going to do a specific example. I'm going to take a look at this first one that I showed you, and we'll do it from the beginning all the way to the end and show you how it's done. Okay, so using this example that we previously saw, this is what the graph looks like. We're going to do this one together, and we're going to do it from the beginning to end. So we have this function, which is the absolute value of x minus 3. Going back to what you may have learned in secondary 5, pre-cal, or even cal 1, that you got to break up this absolute value into 2 parts. The negative part, which is from 1 to 3, and the positive part, which is from 3 to 4. Now, you should already know how to do this, and if not, then you should go and verify or review how we evaluate absolute value functions, because this is extremely important. So therefore, I have my first part, which runs from 1 to 3, and I have my second part that runs from 3 to 4. So I break it up using 2 integrals, the negative from 1 to 3, and the positive from 3 to 4. So now what we're going to do is we're going to evaluate these independently. So let me evaluate this one. So I take out the negative, I leave the 1 and 3, not a problem, and simply find the antiderivative of x minus 3. When I find the antiderivative of x minus 3, I end up with x squared over 2 minus 3x. Evaluate at the upper limit 3, so it becomes 9 over 2 minus 9, minus the lower limit, which is 1/2 minus 3. When I evaluate this on my calculator, or if I can do it mentally, good for you, I end up with a value of 2. So that's the first part. That's the area under the curve between 1 and 3. Now I need to find the area under the curve between 3 and 4. So the second part. So I evaluate x minus 3. The antiderivative is the same as the first one, except that I'm just evaluating it at different points. So my upper limit is 4 and my lower limit is 3, so it becomes 16 over 2 minus 12 minus 9 over 2 minus 9. When I evaluate this, I end up with a half. So we add those two pieces together, and the area under the curve between 1 and 4 for the absolute value of x minus 3 is simply 2.5. I hope that helps. Okay, so we're going to take a look at this example. It's finding the definite integral, or finding the value of 2x dx from -3 to 1. Now, I drew the graph for you, and as you can see, the negative part is larger than the positive part, or let's use mathematical terms, then the non-negative is smaller than the negative. So therefore, I should end up with a negative value. Now here, in this particular case, I'm not asked to find the area underneath the curve, because once again, to find the area underneath the curve, it has to be non-negative. Here, I'm simply asked to evaluate this definite integral. So once again, I break this up into two parts. I go from -3 all the way up to 0, and then from 0 to 1. So first I evaluate the negative, and then I evaluate the positive. We simply find the antiderivative. So if we take the antiderivative of the first one, I get x squared over 2 times 2, which is simply x squared. I evaluate from -3 to 0, and I end up with 0 minus 9, which is simply -9. I evaluate the second part, same thing with the same antiderivative, because it's still x squared, from 0 to 1. Therefore, I get 1 minus 0, which is simply 1. And now in this case, I add those two values. So -9 plus 1 is -8. So the value of this definite integral is -8. It is not the area underneath the curve. It's just simply the value of this definite integral evaluated from -3 to 1. Okay, so practice, practice, practice. I tell my students all the time, the only way you're really going to understand this stuff is if you just simply do problem after problem after problem. So the next video will be the mean value theorem and the average value of a function. That's probably going to be a really, really short video, but it's important that you take a look at these, especially when we give names to theorems. So wishing you all the best, and enjoy.